Hi everyone, I'm Radoslav and today I'm going to be explaining the final problem from the January challenge, which was called Greedy Student, and it was apparently the hardest problem. If I'm not mistaken, around 10 people solved it, and the problem was related to geometry, dynamic programming, graphs, and data structures, so it had like parts from different topics. And yeah, I'm gonna start by first explaining the problem statement, then I'm gonna just basically start explaining the solution. And here I'm going to mention that I'm going to explain my solution, and the author's solution was slightly different. And if you're interested in that, I advise you to check out the editorial. However, the differences come in the later parts of the solution, or more precisely, when we convert the problem to graphs and finding the k largest paths in this graph. So without further ado, I'm gonna explain the problem statement, although this time it's relatively simple. Basically, what we have is, so we have a bunch of points. To be more precise, we have n points, and we also have a k, like k is a given integer. And then we are given the points, and what we are interested is basically just finding the areas of the k largest convex polygons that are formed using those points. I mean, pretty much if we have these 5 points, like this is the sample, and we want the 15 largest areas, we can just see that, well, basically the largest area is formed by the points A, B, C, and D, because E is somewhere in the middle. So yeah, you can clearly see that the area of this thing is 10 by 10, so it's like 100. And we actually print here 200 because we want to just print twice the areas of basically just all polygons. And yeah, the constraint is basically that we want convex polygons. So it actually turns out that the same problem can be found in the literature. However, all papers actually share a solution that works, I think, in a time complexity that's much worse than, I mean, the time complexity that we found in some papers was worse than the solution we are proposing. So yeah, that's a pretty fun thing, I think, because yeah, in some sense, like, this problem is basically a solution to the problem proposed in some paper, which is, I mean, yeah, like we are improving something. But yeah, like, let's just go to the problem. And I mean, before that, actually, just to briefly explain why the problem is pretty hard. It was, I mean, sometimes it's, at least when I was solving it, I had quite a lot of trouble to actually discover how to start. And because, like, we have just a bunch of points, and in a way we want to form convex polygons, and that's not that easy to do. But yeah, let's go to the solution. We are gonna see how to do this. All right, I'm gonna explain the solution in a couple of parts. The first part is gonna be basically how to enumerate all convex polygons so that every convex polygon will be enumerated just once. And yeah, that's like the first part, which is, I mean, like, this is probably because, like, when you are actually trying to find the area of the largest convex polygon, although that's quite easy, mostly because you can just find the convex hull. I mean, like, there's just a very specific way you should begin the problem, and if you don't do that, it's quite hard to actually convert this problem to finding the k largest areas. And more, I mean, like, when I browsed the solutions during the contest, quite a lot of participants actually tried uh, starting with the whole convex hull and then just removing some points to basically just get some smaller areas. And I mean, this is the most intuitive way to start this problem, and I also tried something like that when I thought of the solution. But unfortunately, I mean, we are still not aware of a solution that's basically in those lines. So yeah, I mean, there's a very specific way you should start the problem. And actually, let's get right into it. All right, so let's see how to enumerate all convex polygons if we have some points. Basically, the first part is to actually create all possible directed edges between any 2 points. So let's imagine that we have those 4 points, like it's just like some random 4 points. And the first thing is that we are basically gonna just create all possible edges. And yeah, basically we have, I mean, in this case, we have 6 edges, which are like that, but they're bidirectional. I mean, like, we have an edge in one direction and then in the other direction. So overall, we have 12 edges. And the second thing we do, we actually sort all of the edges by angle. And I mean, like, if you just, I mean, I already sorted them by angle, and the first one will be this green edge in the right direction, then it will be this red edge in this direction, and so on. Like, I mean, if you want, you can stop the video, and yeah, I mean, like, it's basically we just get all directed edges and we sort them by their polar angle. Polar angle is basically just the angle between the OX line and some vector. And yeah, that's basically what we do, and we get those directed edges which are sorted in some order by their angle. And we basically do this because there is a very nice property if we sort all directed edges. And the property is that if we take any path that starts from some vertex v, or by vertex I mean point. So if we start from some point v and we go through some directed edges, so that like if we start from this point, we can go here, then we go here, then we go here, and so on. So the property is basically that if we have something like that, and we only consider paths such that all edges, or like, well, basically the directed edges, are in increasing order of their angle, then we'll definitely have a convex polygon. I mean, that's not very hard to understand because, I mean, just look at the order. The first edge is this green edge in this direction. Then we have this edge, which is from, like, basically this one in this direction, and so on. And the thing is that basically, if we just start from this vertex and we go to something that has a greater order, so here we can only go to, I mean, basically we can't really start with this first edge, but we can go in the other direction with it. But I mean, like, the idea is that we are gonna form a polyline, and the polar angle will always basically just increase. So in the end, we are gonna, I mean, if we end up again in V, so we have like a closed thing, this closed polyline will definitely form a convex polygon. I mean, you can stop the video here, but this is actually one way of counting the number of different convex polygons that can be formed by some points. And it's, I mean, that's basically the way we need to start a problem. It's not a very common approach, although I have seen some problems in the past that have used it. But I mean, I also had some trouble with actually realizing that we should start like that. But it's a good thing to have in mind that sometimes when you actually want to enumerate convex polygons, or just have some task which depends on the convex polygons for some set of points, then a pretty neat trick is to actually just consider all directed segments and then just sorting them by angle, and like just looking at some paths that have, I mean, just looking at some paths that are increasing based on the current edge. I mean, like, based on the angle, not the edge. And this is the property that if we just look at some path, and it will basically be like a convex polygon if it's increasing by the polar angle. And the cool thing about it is that if we look at all paths like that, starting from any point and ending in any other point, we're going to enumerate all convex polygons, and every polygon will exist. I mean, there's like a unique path that that corresponds to every polygon. So yeah, basically like this is the main thing we need to use for our problem. And after that, we basically just need to take a lot of steps that will, I mean, basically like we just, after we have figured this out, we basically just have a lot of steps which will basically just lead us to the solution to the problem. But yeah, to recap, if we sort all directed segments, then we are, and just get like some path that's in increasing order of the angle. So like from some directed edge, we can just go to edges that are greater than it. And also like, obviously the edges should be connected because we want a path. And I mean like in the end, if we again go back to V, so in some sense it's like a cycle that has, that starts at some vertex and then basically just increases the values of the edge. And just by values, I mean like basically the order of the angle. But yeah, overall, like if we just enumerate all paths like that, then we are gonna get all convex polygons. And well, let's basically just use dynamic programming here as, I mean, in a way, we want to count something for, I mean, like we have a bunch of polygons and we want to count like the k largest areas. And I mean, like, you can even notice that we have a bunch of -1s after all of the areas. I mean, like, if we have less than k polygons, we need to print a bunch of -1s. So I mean, like, a simpler version of this problem, if we didn't really care about the values of the areas, would be to actually count the number of convex polygons and to check whether it's less or greater than k. And it turns out that we can actually do this with dynamic programming. Here I'm gonna, for simplicity, I'm gonna assume that our dynamic programming is the maximal area. Although this problem is way easier because the maximal area of a polygon will always be the convex hull. I mean, like, in a way where we basically just want to solve the k equal to 1 case in the beginning. Although, as I said, it has a very simple solution. But let's try solving this with dynamic programming. And we are going to introduce our dynamic programming as dp of I, j, and k, which will mean that this thing will actually correspond to the area of the maximal area of a polyline that starts from vertex I, ends at a vertex j, and only uses some of the first k edges. So in some sense, we just get like a naive quadratic solution because at this point, we can basically either use k, like the k plus first edge, or just like discard it and keep the current ij. I mean, it's basically just like there are a constant number of transitions because like we can either use the new edge or just discard it. However, we can notice that every edge can update up to n dynamic programming values. That's because like, I mean, imagine that we're going to just substitute I as start because like that's the start of our path. And then we have some, like the kth edge is basically from x to y. And I mean, like, we basically just need to update the dp start yk. So it's like a polyline from start to y using the first k edges. And we can, I mean, the previous dp we are going to use is basically the polyline from start to x, which was like the previous vertex. I mean, we basically just use the edge from x to y. And we can just use the previous k-1 edges. And then we need to add the cost of the edge from x to y. Here, cost will mean basically the contribution of this edge to the overall area. And I mean, obviously this cost will just be the determinant of the matrix that's given basically by the 2 points, which are, I mean, the x point and the y point. And also, like, if you want to argue about it in terms of cross product, then this cost will just be the cross product between those 2 points. So yeah, I mean, like, basically that's our formula, and obviously we need to just change it for all start points because, I mean, those are all of the affected values. So yeah, basically that's pretty much it. And this way we get like a cubic solution if we remove the last dimension, because we can just use the previous DP table and just update n number of values in it. So yeah, like this way we can get a cubic solution. And something that we should notice, actually, it's good that I actually have notes, because maybe I would have forgotten about that, is that, all right, if we have like this edge which is from x to y, if y actually coincides with start, we don't really want to update the start DP value, but we actually want to update some separate value, which we are going to call a sync value, because in some sense if from x, like if y is equal to start, this means that we basically just closed our polygon. And I mean, if we have closed our polygon, this means that, I mean, if we have closed our polyline, this means that we now have a polygon which just starts at this start vertex. And yeah, these are actually the objects we want to reach. And yeah, I mean, like, we just have to make sure to handle the case where y is equal to start. That's just like as a note I have left for myself. Okay, so to recap, right now we have a cubic in N dynamic programming solution that enumerates all polygons. I mean, like, currently it doesn't really enumerate them, it basically just finds the largest area. And what we have to do here is to basically notice that we can convert our problem to a graph theory one. And yeah, the way to do this is actually to, I mean, it's basically just like, let's go back to this slide. I mean, we have this formula, and this means that we basically just want to update this vertex by the maximum of, I mean, basically we have just some edge and some other vertex. It's just like the trivial construction when you have the, because like obviously this dynamic programming is a directed acyclic graph. So, I mean, we have a trivial construction to get from this dynamic programming to this directed acyclic graph. And the only problem is basically that we need to, I mean, like, we have a cubic way to solve the dynamic programming. However, if we just want to construct the graph, it will have quite a lot of vertices. I mean, it will have like n to the power of 4 vertices. However, the thing is that we can avoid creating all of the vertices. And I mean, in some sense, what we are going to do to create the graph while building this initial DP for maximal values, we're only going to create a new node when we need it. And yeah, I mean, like, initially we create this DP, and in some sense we create the graph dynamically. Basically, if we need to update some vertex, if we need to update some node, we basically just create this vertex. By node, I meant if we want to update some DP value for 2 cells, we just create a new node. And because like you can actually notice that the number of edges can be quite large, we in a way use compressed vertices to just kill the small edges. I mean, it's basically just converting the previous solution, which was the cubic one, where we just remove the current edge dimension here to, I mean, to a graph. It's not that hard, like that. Basically convert, in my opinion, the hard part was actually coming up with the DP, and then the other, like the later parts of the solution, which I still haven't covered. But like actually going from the DP to the graph is relatively easy. So I'm not going to go into too much detail about that. So yeah, I mean, like, it's possible and it's relatively easy to avoid getting the n to the 4th power vertices. And yeah, pretty much the idea is to just create nodes only when we need them. And yeah, then the second tricky thing, I guess, is to, I mean, it's basically to not confuse the starting DPII nodes with the ending DPII nodes. Like, it's basically the thing I mentioned, where we don't really want to, I mean, after the first time we have start equal to y, we don't really want to continue doing the DP. We basically just want to stop DP. So that's why we create separate vertices for the starting DPII node and the ending DPII node. And we are going to call the later sync nodes because, yeah, in some sense, this is our ending. And we are going to call the starting ones basically source nodes. And the final part is basically we just create a super source which is connected to all source nodes and a super sink that's connected to all sync nodes. And the edges between those are obviously 0 because, I mean, the super source is just a way to connect everything to the vertex. And yeah, now, if you think about it, our problem is basically we have this large graph, and what we want is to find the k largest paths from the super source to the super sink. And the thing is that we have n cube edges and n cube nodes. This is after we have built our graph. And I mean, like, obviously the graph is weighted because else the problem wouldn't have made a lot of sense. But yeah, I mean, like, this is around 1 million or like a couple of millions. So, I mean, yeah, basically, like, we have a relatively large graph and we want to find the k largest paths in it. And yeah, they're like, I mean, after you read this problem, it seems that it will be quite famous. I mean, like, you just basically need to find the k largest paths in the graph, and this would have definitely been covered in the literature. And that's indeed the case. You can basically just find a paper and implement this thing, which, I mean, this is a doable thing. This is something you can do, but you can also like try thinking about a solution and figuring an algorithm by yourself, which is basically what the author did. And he uses some persistent segment trees for that. You can check out the editorial. It's relatively simple, and it basically just covers some of the papers. I mean, like, some of the papers basically just do what the author is doing. And yeah, I mean, like, you can solve this problem with persistent segment trees, but also you can, I mean, in a way, our graph is kind of specific because it was constructed from geometry and it wasn't really constructed. I mean, it's not really a random graph. It's just basically like a graph that's constructed from this dynamic programming variation, which I mentioned. And in a way, there are actually some specific things about it. So you can actually use them to your advantage and find an easier solution. Although, like, one can argue whether it's easier or not, but in my opinion, it was slightly easier compared to the other solution. All right, so basically what you want to do. I mean, here I'm going to explain my solution, which uses data structures. And the thing about it, what I meant by using this specific graph structure to your advantage is that because of this thing, a very naive implementation actually would be relatively fast for this problem. So what do we actually have? Let's actually go backwards, starting from the super sink, and maintain a max heap of all paths that start at a given node and end in the sink. This may sound kind of weird, but it's basically just we have a heap for every node, and it will represent all of the paths that start from it and go to some other node. And yeah, in some sense, like, the heap for the super sink, it's just 0 because we have like just a single path from the super sink to itself, which has obviously, I mean, obviously the weight is 0 because we have no edges. And yeah, I mean, that's the start of the solution. And what we actually want as we go backwards is to build this heap. And to build it, we are actually going to use the adjacent heaps. Or in other words, let's have some vertex u. And what we want is basically the heap of u should be equal to the union of the heaps of its adjacent nodes. So I mean, like basically if we have an edge from U to V, and I mean, to construct the heap of U, we can basically like just choose the, I mean, it's basically just like the simple dynamic programming, which is on the graph DAG, but instead of just computing the maximum here, we're gonna compute a heap. And like, instead of just having a maximum here, we are gonna have a union. And yeah, I mean, basically what we have is that the heap of U is basically the union of the heaps of the neighbors. We've added the cost of the edge from U to V to them. That's just like the formal definition of getting the heap. And obviously then, I mean, before that, obviously the answer will be the heap of the super source. I mean, like, we basically just extract the heaps like that, going through the topological order. And yeah, then we have the heap for the max heap of all paths that start in the source and then in the sink, like the super source and super sink. And I mean, like, this is basically our problem because we just want the k largest values in this heap. So yeah, now the only problematic thing is to actually implement those operations, because like we need two operations which are adding some value v to all elements of a heap, because here we have like some other heap which is the neighbor, and we basically just need to add the cost of the edge from the current node to that neighbor to all elements in this heap. So yeah, this is the first element. This is the first operation, which is basically just add some constant to all elements of a heap. And then the second operation is basically just to merge or unite two heaps into one. The thing is that like here we have a union of a bunch of elements, but that's pretty much the same as uniting the first and the second, then the result with the third, then the new result with the fourth, and so on. I mean, like, if we can unite two heaps, then we can unite as many as we want. And yeah, also there is something that we are missing, and it's that we also want this structure to be persistent, because we can notice that the v here can appear many times as a neighbor. So in other words, I mean, we have a DAG and not really a tree. So the v here can appear multiple times, and we want to keep this the initial version of the heap. So yeah, in some sense, what we want is a randomized heap, because I mean, to have the second operation, which is the merging of two heaps into one, we need a meldable heap or a randomized heap. Like, the most common way to do it is to just use a randomized heap, and we also want it to be persistent. So yeah, we basically just want to make this heap persistent, which is pretty easy. Every time we have some operation, instead of just overwriting the node, we just have to copy the node. It's pretty much one additional line to the implementation. And the other thing is as we want to add v to all elements of a heap, we are going to have a lazy for our heap, which is again pretty easy to do. We just keep an additional variable for every node. And to combine the laziness and the persistence of the heap, we just have two additional lines, which are, when we push the lazy, we create copies of the nodes. And that's pretty much it. Even though it sounds kind of hard, because it's like a lazy persistent randomized heap, which is, I mean, it may sound quite scary, but in reality it's a very simple data structure. And yeah, even though it's persistent, the time complexity is pretty good. But let's actually try analyzing the complexity in some more detail. I mean, we already figured out that every path actually corresponds to some convex polygon. I mean, like every path from the beginning to the end. And also every path, like every intermediate path that starts at some vertex and ends in the sink, actually corresponds to some polyline. And obviously we can see that there are at most 2 to the power of n different polylines, because I mean, like, every polyline is defined by a set of points, and they're at most 2 to the power of n sets of points. So this means, because we have this bijection between the paths and the number of polylines, that the number of basically this means that the total number of paths is at most 2 to the power of n. And I mean, by using the analysis of the randomized heap, we know that the expected depth of some heap would be basically the logarithm of its size. And as we know that the size cannot exceed 2 to the power of n, don't forget that our heap is actually persistent. So in reality, we won't really go through the whole heap, but I mean, if we actually could just print the whole heap, the size would have been at most 2 to the power of n. Then the depth of our heap would be logarithm of this thing, which is 2 to the power of n, which actually turns out to be linear in n. And also in practice, it turns out that the depth is around 50. Like, I ran a couple of experiments, and I mean, it's even less than 50, but just for the sake of being sure, it's relatively low. I mean, like, in the test I did, it was like around 30, but let's say it's 50 because, yeah. I mean, and this is like the final depth. But by depth, I mean the maximum number of operations we did in the randomized merge for the heaps. So yeah, I mean, like, this way every merge will be linear in n. Don't forget that n is, even if it was O(n), n was around 120, so this is doable. Like, we have a million nodes, and having like 100 million operations is relatively low for this problem. However, even if we want to speed this up, we can also notice that we can prune our heap so that, because like we only care about the k largest numbers. So what we can do is basically just prune our heap so that it doesn't really have a lot of numbers in it. And one way to do this, which is a heuristic, but it's a very simple heuristic, is to basically just choose some maximal value. Actually, not maximal, but like minimal value. And we are going to just discard all values in the heap less than this minimal value. And I mean, this way we can, I mean, if we approximate this minimal value of the k thing, we can ensure that we'll have approximately I mean, like, we're basically going to ensure that we have around k elements in the heap. I mean, to be sure, we should have like 10 or 20 times k elements in the heap. And yeah, like, this way all of the operations will be logarithmic in k, which is very fast. And I mean, like, the author solution basically does that, but with some other data structures. However, yeah, I mean, this wasn't really required because, I mean, it's kind of tedious to actually prune the heap because you don't really know the order. You just know the maximal, and you know that the children are smaller than the parent. But yeah, I mean, like, for this problem, it was enough to actually just use this linear solution, which is linear mostly because the structure of our graph is pretty nice, and because like the total number of polylines can't exceed 2 to the power of n. So yeah, that's pretty much it. In the end, as I said, we have like a heap in our super source, and we just want to get the k largest numbers in it. So we have like two ways to approach this. The first one is to implement some remove max operation for this persistent randomized heap, which can be done by basically just, I mean, we extract the root and then we just merge the children to get a new heap, and so on and so on. I mean, it's not really implementing a new operation, but yeah, that's one way to do this. Also, another way is to just use a normal heap or a priority queue and start from the root and do something like Dijkstra on the heap to just like go to the, I mean, to basically just extract the numbers one by one. Both of them are fine. You can just use whichever you want. the complexity will obviously be, for the first one with removing the max, it will be k multiplied by the depth of the heap, and the other one, which is like with the priority queue or the normal heap, it will be k log k. All right, so let's now go to the overall complexity, and this is how I'm going to end this problem, editorial for this problem. So initially we need to build this graph, so that's like cubic in n. Then we need to build heaps. Here f of n and k is basically the complexity of the merge, because the merge is the complicated operation, or like the slow operation, as the addition is just like you increment the lazy flag for a certain node and you push it once, so it's constant. So yeah, I mean, like f and k is basically the complexity of the merge. By just using some simple analysis, we can get that f and k is definitely less than n, because the total number of parallel lines is 2 to the power of n. However, in reality, it's like much less, and also you can use some pruning to reduce this even further. So yeah, this is like fast enough again, and then you just have like k log k complexity to find the answer if you use just a priority queue, or k times n, or actually not k times n, k times f and k if you use the first approach with removing the max. But yeah, overall, like this approach passed in around 2 seconds without any optimizations. So like, I mean, it was just the first implementation, which I didn't try optimizing for speed. And yeah, you had like a 5 seconds time limit, so that was fast enough for you. I mean, this solution I think is pretty cool, mostly because you can also adapt it to the smallest k areas, or like just any k areas. So yeah, I mean, it's pretty cool, and it's a good thing to know that you can actually solve the k largest or k smallest paths for a directed acyclic graph with a randomized heap, which is persistent also. But yeah, that's pretty much it.